Otherwise, you can't do it because I'm not having to. All right, so hope everyone had a good weekend. Last week before our little reading break, so that'll be good. Catch some breath before the home stretch. Okay, so what we were working on last time were, the essence of it was to try to figure out if we have a current distribution in some region of space, could we determine what the magnetic fields created by that current would look like? And we ended up writing down this relatively complicated Biot-Savart law. We applied it to the case of a long straight current. And what we found is, so here's a long straight current where the current I is coming out of the screen. And what we found is the magnetic field lines loop around that current, and they have a magnitude that decreases as 1 over s, where s is the distance, the perpendicular distance from our current to some observation point. So if you remember, when we did that calculation, like it was pretty difficult even for basically the simplest possible current distribution that we could imagine. And so one of the things we'll work on today is to try to see if we can come up with another method for calculating magnetic fields from current distributions. It's going to be Ampere's law, and Ampere's law is like the analog of Gauss's law, which we had for electric fields. The other thing that we saw last week was the so-called continuity equation, where the divergence of J was equal to minus d rho dt. So let's think about what that means. We'll think of some volume that has some steady current in it. And if the current is steady, that means all the charge that leaves that volume is replenished at some other point in that volume. And so its charge density would be 0. In that case, the divergence of J would be 0. That tells us how much current is leaving our volume. But if we have equal current or equal charge, leaving and entering, then this d rho dt would be 0, and our divergence of our current density would be 0. Okay. So what I want to do today is really two things. One is I want to write down the divergence and curl of the magnetic field like we did for electric fields. So for example, for electric fields, the curl of E was equal to 0 and the divergence was not 0. Okay, it depended on the charge density. So let's see how we can do that. We're going to start by taking a simple approach, and then we'll try to generalize it from there. All right. So let's try evaluating the following integral. So it's the line integral of b dot dl around a closed path. Now, it may seem arbitrary that I just randomly wrote down that integral, but really what I'm going to try to get at is the curl of b. And so how can we relate this to the curl of b? We can use Stokes' theorem. And so this is going to be equal to the curl of b dot dA, and this is Stokes' theorem. And this would be over some surface S. Okay, so we're going to evaluate this integral, which is called the circulation. And we're going to relate it to the curl of B. Okay, so let me draw that picture that we had where we have some current coming out of the screen, and then we had a magnetic field that was looping around, and I'll draw just a couple of the lines. So by the right-hand rule, if I put my thumb in the direction of the current coming out of the screen, my fingers curl in the direction of the field, and so the magnetic field must be in this kind of orientation. What I want to do is I want to pick my integration path so that the integral is easy to evaluate. So given the geometry of this magnetic field, what kind of path should I choose? I'll choose a circular one. Where should I put the center of the circle? Right at the current, right? Yes. Now, in principle, I could choose any path I want, right? And it would turn out that I would get the exact same answer. It's just that if I make a smart choice of the integration path, then I save myself a lot of work. And so we're going to select an integration path that matches the symmetry of B. Just looking ahead, when we do get to Ampere's law, what we're really doing is we're picking the shape of our Amperian loop. So that's equivalent to picking a path to integrate around. And so this is going to be my integration path. I might as well choose the direction to be in the same direction as the magnetic field, just to avoid dealing with unnecessary negative signs. And so this is going to be our integration path. And so my DL will be tangent to this path. Okay, so that's fairly easy to do. So in this case, for the path that we've chosen, DL has some magnitude, just DL, and its direction is in this phi hat direction. And B, we calculated last time, and it was mu naught I over 2 pi s. And it was also in this phi hat direction. So if I want to do this path integral at the top, I need the dot product of B and DL. So therefore, B dot DL is going to be equal to, well, it's mu naught I over 2 pi s. Phi hat times phi hat, or phi hat dot phi hat is just going to be a 1. And then we just have a DL. Okay. Now, if we make the additional assumption that the current is constant, S is the distance from the current to my integration path. And because I've centered that thing, centered my path on the current, S is a constant everywhere along my path. And so all of this stuff is a constant on our chosen integration path. And so these features of our choice for this integration path are really things that you're going to want to look for when we do get to Ampere's law. You want to be able to evaluate this dot product easily. So you want your DL and your B to either be perpendicular, so that the dot product is 0, or parallel, so the dot product is just the product of magnitudes, regular multiplication. And then you want to have the stuff that's in here be, as much of it be constant as possible so that you could pull it outside the integral. Okay. And so if you make those good choices, then this integral that we're trying to evaluate is just going to be the integral around the closed path of mu naught I over 2 pi s dl. But everything is constant, so it all comes outside. And this is just saying, add up all the little displacements around your path. And so that's just going to be the circumference of our integration path. Our integration path was a circle of radius s, and so it's equal to 2 pi s. And well, what's going to happen is this 2 pi s is going to cancel with that 2 pi s. And so, which is the same thing as that integral. And so therefore, what we find is that this circulation integral, this is called a circulation, is just equal to mu naught times I. Okay. This will eventually be what we're going to call the integral form of Ampere's law. But what we've done so far is not that impressive, because all we've done is we've shown that it's true for the special case of a long straight current. What we're going to try to do is we're going to try to generalize this result so that this will try to show that this is always true. So far, we've shown that this result is true for a long straight current we want to generalize for B due to any steady current distribution. Okay, and once we do that, we'll call this Ampere's law. In fact, this will be the integral form of Ampere's law. All right. So note that last time we showed that J dot dA integrated over some surface S was equal to I. So what I want to do is I want to use this expression for our I, and then here we're going to apply Stokes' law. Okay, and so let's see what happens if I do that. So we're going to have Stokes' law says that this line integral is going to become a surface integral. So there's S, and then it's the curl of B dot dA is going to be equal to mu naught times I. But I, we're going to write this one. And in fact, let me go ahead and take this constant inside the integral. So we'd have mu naught times J dotted with dA, like so. And so what we have is the same integral, and it can only be equal if the integrands are equal. And so these must be equal. And so therefore, the curl of B is equal to mu naught J. Again, this result is true for our special case of a long straight current. We're going to try to show that this is generally true for B due to any distribution of current. Okay, and this will be the differential form of Ampere's law. All right, and then this one will be the integral form of Ampere's law. Okay, so what we'll actually do is we'll show that this equation number sign is generally true. And then if this one is true, then the integral form is definitely true because that's just a Stokes law conversion. All right, so let's see if we can do it. So the goal is to reproduce this equation number sign, starting from the general Biot-Savart law. Okay, so we'll write down this Biot-Savart law. There's some constants, mu naught over 4 pi. It's an integral over some volume of J. Now remember, J is our current density. It's the source of the magnetic field. And the vector r prime locates the source relative to the origin. So r prime is scanning over our current distribution. And so then we have cross with this curly r over curly r squared, and then this is d tau prime. So the other thing I want to emphasize before we go further is that J is a function of r prime. This script r is r minus r prime. And then we're going to integrate over primed variables. Once I complete that integral over the primed variables, the only thing that survives is the r dependence. And so that's why B is a function of just r. It doesn't have any primes in it, right? This is the magnetic field at the position of our observation point. That's important because what we're going to do is we're going to take the divergence and curl of this expression, and we have to know that the del operators are going to act on unprimed coordinates, and the integral is over primed coordinates. And so we're going to have to keep that straight. So let's make some notes about that. We're going to integrate over the primed coordinates, which locate the source currents with respect to whatever the origin is of our coordinate system. And then we're going to want to find, one of our main goals will be to find the curl of B, but we'll also look at the divergence of B. That's actually going to be the easier case. And when we do that, this del operator takes derivatives with respect to the unprimed coordinates. Which locate our field point. All right. So let's give it a go. We're gonna run into, you can see, if I take the divergence or curl here of this integral, then I'm going to end up with either the divergence or the curl of the cross product of two vectors. And so that means I'm going to have to use product rules, and there's these product rules for the divergence of a curl, and there's products rules, for the divergence of a cross product, and there's different product rules for the curl of a cross product, and we're going to have to make use of those. All right, so let's start with the divergence of B. What's that going to be equal to? It's going to be the divergence of, the Biot-Savart law. All right, so we're going to take the divergence of that whole thing. Now, what we can do is we can say, look, I'm integrating with respect to primed variables, and I'm taking derivatives with respect to unprimed variables. So I can take my del operator inside the integral. And so let's do that. This is going to be mu naught over 4 pi, the integral of the divergence of, and let me write it this way. I'm going to write it as j of r prime, and then it's going to be the cross product with r hat over r squared. I'll write it like this, d tau prime. Okay. So if you look at Griffith's front cover, there are listed a bunch of product rules. The one that we want is product rule number 6. So apply product rule 6 from Griffith's cover. Okay, so if we do that, we're going to get, so it's going to be r hat over r squared dotted with, turns out, the curl of j, and then it's going to be minus j dotted with the curl of the other vector, which was the script r hat over script r squared. All right. What's this one going to be?
Yeah,
Why?
because we're taking derivative with respect to things that don't exist.
Yeah, this depends only on primed coordinates. This is a derivative with respect to unprimed coordinates. Okay, so this is 0 since we take derivatives with respect to unprimed coordinates. And j depends only on the primed coordinates. All right. This one's a little more tricky, but if you look up the curl in spherical coordinates, or I guess maybe we should say cylindrical coordinates if we're thinking of a long wire or whatever coordinate system you want to look at. If you look up the curl, it's going to have things, let's do spherical. It'll have things like derivative with respect to r of the theta component minus some derivative with respect to theta of the phi component and all those things. It mixes up the different components. You never have in a curl like the r derivative of the r component. But this vector has only components in the radial direction, and they don't depend on theta or phi at all. And so all of these derivatives are going to be 0. So this one is going to be 0. And this is going to be since the r hat over r squared, which we could write as vector r over script r cubed, has no theta or phi dependence, and no theta or phi components, say in spherical coordinates. Okay. So we did our product rule and both terms ended up being 0. So that means that this whole thing is equal to 0. And so therefore the only conclusion is that divergence of B is equal to 0. And this is completely general. We started with the Biot-Savart law, which we can apply to any distribution of currents. And so this is true for all B due to steady currents. All right. So what we'll do next is the more difficult one. And so the approach is exactly the same. We're going to start with the Biot-Savart law and then take the curl. We'll have to use a different product rule. And this time, not all of the terms will vanish. So let's start on a fresh sheet here. So what we'll do is next consider the curl of B. Okay, so curl of B is going to be equal to mu naught over 4 pi. This time I'm just going to take the curl inside the integral right away. We can do it for the exact same reasons as before. All right, so Biot-Savart law had this current density crossed with r hat over r squared d tau prime. All right, this time we have to use product rule number 8. All right, and if we look it up, what we're going to find is the following. We'll get the second vector, which is our script r vectors, and it's going to be dotted with the following. So there's the del operator, and then that's acting on our current density. And then we get the same thing. We just switch the orders of the two vectors, r hat over r squared. Okay, good. What's the first term going to be? We have these r derivatives acting on j. So for the exact same reason, we say j depends only on the prime coordinates. We're taking derivatives with respect to unprimed coordinates. So this is going to vanish. And we have the second term to deal with now. In fact, I got ahead of myself. Product rule number 8 doesn't have 2 terms. It has 8 of them. And so I didn't, sorry, not 8. It has 4. It has 4 terms. It's product rule number 8, which has 4 terms. So let's just write down the full product rule before I start killing off terms. So we know one of them is going to be 0. Which other one is going to be 0? Second, third, or fourth? Third, no, the third one's a special one. The last one, yeah, that's right. So here is del operating on just the current density, and so that one has to be 0 as well. Okay, so we have these 2 remaining terms, and let's deal with them one at a time. So actually, so someone already said something about them. Where have we seen this before? We saw that one. Do you remember? Does anyone remember? What is like this r hat over r squared? That's kind of like the electric field of a point charge, right? What was the divergence of a point charge? Yeah, it's electrostatics. Where was that divergence non-zero? Yeah, like right at the origin, right? And so what was this thing? It was the delta function, that's right. This thing we saw before, and it was 4 pi times this delta function. Okay. All right. So let's see then, what are we left with? The curl of B is going to be equal to let me do this term first, the third one, just because it's the positive one. We have a 4 pi here. It's going to cancel with the 1 over 4 pi in front of the integral. So we're going to get a mu naught times the integral of, let's see, j of r prime times the delta function. And let me write the delta function as, instead of script r is just r minus r prime. And then we have a d tau prime. I'm going to leave a bit of space, and then we'll write down the second integral that we'd have to do, minus mu naught over 4 pi, the integral, and then what is it? J dot del. Okay, so it's some complicated thing. J of r prime dotted with the del operator, and then it's r hat over script r squared d tau prime. Okay, good. So this is what we're left with for the curl. What is the first integral going to evaluate to? Well, almost. That's almost exactly right. We're integrating over the prime variable, so we'll end up with, after the integral, not a primed variable. It'll depend on just the unprimed coordinates. And so instead, it's going to be j of r prime evaluated when r prime is equal to r. So this, by the property of the delta function, is j of r.
Like it's that, but like then normally the one integrated minus the other one.
So what the delta function is going to do is the delta function is going to, yeah, so delta function selects value of r prime such that what's inside the delta function is equal to 0, and so this is r is equal to r prime. Another way of saying that is the delta function is symmetric, so if you reverse the sign, the function doesn't change. Yeah. Okay. Good. Well, if you look at that, this is the curl of B is mu naught times J. I should put my vector symbol on there. And that's what we're trying to show. And so this would work out nicely if we can show that the second integral is equal to 0. So let me highlight this, and I'm just going to say this is going to be integral I2. So it's the second. So maybe I shouldn't use I, because that's confusing with current. Let me call it integral 2. So we will show that integral 2 is equal to 0 such that the curl of B is going to be mu naught J. And then if we can do that, that was our goal. So then we would have the curl of B is mu naught J, differential form of Ampere's law. And we can apply Stokes' theorem to that and write down the integral form of Ampere's law. And then the divergence of B, we've already shown is 0. So we have to work on this integral. And so let's do a bit of an aside, because there's a bit of a trick that we're going to play. Aside. I want to consider the integral d by dx of f of u, where u is x minus x prime. All right. Now, if I want to take this derivative, what do I have to do? The u is a function, so I have some function of u, and u is a function of x. So what tool do we have? Chain rule. So by the chain rule, this says this is df du times du dx. Okay, what's du dx? 1, exactly. So this is 1. And so that means that this is just df du. So fine, that's no problem. Next, I want to consider the same thing, except I'm going to take a derivative with respect to x prime of this function f of u. Well, it's the exact same thing. It's just chain rule again. So this is going to be df du, and then it's going to be du dx prime. This part is obviously the same. What does this part give? -1. So this is -1. And so this is equal to minus df du. And so the reason we're doing this is just to see that these two are the same, just a sign change. And so that means then that if I take df by dx prime of f of u, that's the same thing as minus d by dx of f of u. So this is the little result from our aside. Why did we do that? It's because if we go back to this integral number 2, we have a del derivative acting on a function of r minus r prime, which is the same thing as our function of f of x minus x prime. It's just a three-dimensional version of it. And so by the same logic, we're going to change this to be a derivative with respect to primed coordinates. It's going to cost us a minus sign. So by the same logic, the thing that we have to evaluate in integral 2 is equivalent to minus the del derivative with respect to the prime coordinates. All right. Oh, sorry, what am I doing? I'm just being dumb. I'm being dumb, like usual. So this is acting on, we need it to be acting on, first of all, it's not a divergence, it's just a gradient. And it's acting on script r over script r. We need the function to be a function of r minus r prime for this to work. So that's better. All right, so that's the end of our aside. Now let's go back to integral number 2 and see if we can do some work on this. I'm going to keep all of this stuff in integral number 2. I'll keep the little constant that's out front, but maybe not the minus sign. Okay, so therefore integral 2 becomes, well, let's see, there's a mu naught over 4 pi out front. Integral, so our j was here. So I put the j in the wrong spot when I first was writing down that identity. But now what we're going to do is we're going to put a prime coordinate system here, and then we'll pick up a negative sign, and then this is going to act on the curly r's and d tau prime. All right. This is a bit of a nasty looking thing. So what we're going to do is we're going to try to break this into components. And so, for example, we're going to write down just the x component of the script r factor, and we'll see what happens. So let's consider just the x component of this thing in Cartesian coordinates. All right. So we're going to have the current density dot product with this thing. And then we're going to have just the x component. And I'm going to use again this result that we already used once. That I can write the unit vector as the vector divided by its magnitude. So this becomes a regular vector, and then we get an r cubed in the bottom. All right, so if I take just the x component of vector r, that's what we end up with. And now we have to do another product rule. And the product rule we're going to have to do is product rule number 5. Product rule number 5. Okay. So if you look up product rule number 5, what we're going to get is the divergence, this thing, multiplied by J. You know that it has to be a product. This is now a scalar because we've taken just the x component. So if I want to take the divergence of something, I have to take the divergence of a vector. So it couldn't just be the scalar by itself. All right. And then there's a second term. This one does have only 2 terms. It's the scalar that we had. And then it's times just the divergence of this thing. All right. Now, previously, when we were looking at derivatives of this function of r prime, we said that these were going to be 0 because these were derivatives with respect to unprimed coordinates. But that's not the case anymore. I still want to make this 0. Does anyone know why it would have to be 0? Steady currents. So if we go all the way back, we said one of the things that we looked at last time was this continuity equation and the Biot-Savart laws for steady currents. And for steady currents, the charge density is a constant. And so the divergence of J is 0. So that's exactly right. And so this one will be 0. This is 0 for steady currents. It's the continuity equation with d rho dt equals 0. All right, good. So therefore, what we're left with, the x component contribution to this int 2 is. All right. So we're going to have integral over some volume of, well, where is it? It's right there. It's this divergence of x minus x prime over script r cubed. And then there was a j of r prime d tau prime. All right. So that's the beast that we're trying to work on. Well, who has an idea? What could we do here? We have the divergence of something inside a volume integral. What does that kind of remind you of? Yeah, not Stokes theorem, but divergence theorem. That's also exactly right. Okay, so now we apply the divergence theorem. I know this one's a lot of work. We're just trying to show that we're going to get a 0. We're almost there. Apply the divergence theorem. Okay, so what happens when we apply the divergence theorem? We end up getting a surface integral of all of this stuff that's inside. So it's x minus x prime over script r cubed j of r prime, and now it's this dA prime. All right. What we can do is we can pick whatever surface we want, as long as it bounds the entire current distribution, right? So let's just think of the problem that we have at hand. We have some volume of space where there's some given current density in this volume. That volume is surrounded by some bounding surface. We can pick that bounding surface to be whatever we want, as long as it contains all of the current density, and the d rho dt is equal to 0. So there's no net charge leaking out of or entering our surface. If I pick the surface big enough, I can always arrange it so that on that surface, the current density is equal to 0. If it's not equal to 0, I just pick my surface to be bigger and bigger and bigger. And if this is 0 everywhere on my surface, then the integral is going to be 0. Okay, so that's the little trick. So this is the surface that is bounding the integral in the Biot-Savart law that contains the current density. Okay, so we choose the surface to be large enough that j of r prime is equal to 0 everywhere on the surface, such that integral 2 is equal to 0. We've only done the x component, but nothing changes about the argument for the y or z components. Okay, so it's similar for the y and z components. All right, so then the summary is the following. Here are the important results. The divergence of B is 0, and the curl of B is equal to mu naught J. This is valid for all magnetostatics. So this is any steady current situation, not just a long straight wire of current. Okay, this is Ampere's law in differential form. Let me just remind you of Ampere's law in integral form. In fact, we're now in 5.3.3. Ampere's law. Okay, and so we've kind of already done the work. Is mu naught J. So let's integrate. We're going to integrate so that we can use Stokes' theorem. So what we're going to do is we're going to choose some surface area, like so. And we can kind of draw a picture of what that looks like. Let's imagine that I had some surface. It could have arbitrary shape. It doesn't need to be a flat surface. I just can't draw a kind of surface with some curvature on it. So this is my surface. In fact, let me just put that my surface is what's inside here, and we can shade it some color. And then what we're imagining is that we've got a certain amount of, well, let's do Stokes' theorem first. So Stokes' theorem would say that this would be equal to the integral of E dot dl around the boundary. And so my boundary is just the circumference around the surface. This is my boundary. Okay, so that's Stokes' theorem. We still haven't done the other side of the curl of B. And so that means, what do we have? We have the circulation integral, which is what we started with at the beginning of class for the long straight wire, is equal to mu naught times J dot dA. But that's just mu naught times I. And so what I want to do with this picture is interpret this J dot dA integral. So we could imagine that in general, we have some current density in some region of space. Maybe some of them are going through our surface, and maybe some of them are missing our surface, but these are lines of some current density. And what we're doing is we're seeing how many of those actually penetrate into our surface. That's what this integral is calculating. So for example, if I had the screen was my flat surface and my current density was going parallel to that screen, none of it would pass through the screen and we'd get 0 for the integral because the dot product would vanish. But if I have some lines actually penetrating into my surface, then I get non-zero dot products and a non-zero result for this integral. And in fact, it's the total current I that crosses the surface is the integral of J dot dA. So this is just equal to I. And so therefore, what we have is B dot dl is equal to mu naught I is the integral form of Ampere's law. And to make it seem more similar to Gauss's law, you would usually say this is I enclosed. This is how much current penetrates through or passes through our surface. So this is the total current passing through our surface, S. All right. Yeah. Yeah, you're right. So that would be, so maybe what I should have done is maybe if I well, I don't want to remove those. So let's see, the curl of B, yeah, the current density would have to be 0. Yeah, you're right. I should have picked my surface so that we capture that current. So here, let me see if I can get rid of this one. Yeah, I agree with you. Thank you. That makes sense. So I'm going to expand the surface so that all of these lines will. Yeah. So they're going to puncture through my little surface. So we're calculating the flux of this current through this. Yeah. So at the boundary. So if we go back to this thing, this is, I guess, so sorry, let's back up. I'm confusing things and it's not working well. So we have to think of this, we started with an integral over some big volume. So let's imagine there's some big volume and inside there's some non-zero current density at some points. And then here we're asking, like, let's think of a balloon. So we inflate a balloon. So there's some current inside the balloon. And then we're asking here for some integral of the current density over the surface area of the outside bounding surface. So we're saying that at that bounding surface, we have a no current density because it's all contained inside the balloon. So that integral will go to 0. What we're doing now is a little bit different. I think I'm going to put my lines back. Now we have some two-dimensional area. This is just a different integral, right? It's not related explicitly to that previous problem. And now when we do Stokes' theorem, we have just this like one-dimensional boundary here, which is different than having the surface of it. Yeah, good. Okay, that's a good question. I mean, obviously, I got a little confused as well, but I'm going to put these back because we're counting only the current that's going through this surface. All right, good. So we have like 20 minutes left, and what I want to do is I want to do some actual examples. So enough of the derivation for today. Let's do some examples. Example. Let's find B due to a long solenoid. Okay, so a solenoid, let's imagine that we take some kind of cylindrical object. This is just going to be a former. And then what we're going to do is we're going to take a wire and we're going to coil it around our little former here so that we get this spiral. Oops. So, and then we'll come down and we'll have one more coming. All right, and so I'm going to send in my current in this direction, like so, and so it's going to come down here. So this is current I. All right, before we actually go and do Ampere's law, what I want to think about is this is like having a bunch of individual current loops side by side by side by side. So if we take a bunch of current loops, stack them side by side, that's one way of building a solenoid. So this is like a series of current loops. So if I draw one current loop, maybe it'll look something like this. So here's a loop of current. And if we did right-hand rule, so let's see, what am I doing? My current is coming up, let's say, in front of the screen. So I'll make an axis here. So there we go. So my current is doing this. So that means by the right-hand rule, the magnetic field through the loop is to the left. All right, so then I have a magnetic field that's doing something like this through the center. But then if you were to draw some of the field lines off center, what you would find is that they would make these kind of loops. Of course, it's a three-dimensional structure, but I can't draw in all 3 dimensions. So this would be looping like so. And so here's the magnetic field. So what I want to do is I want to draw a sequence of these current loops, and I want to see how their magnetic fields add up at various points. All right, so let's consider, I'm going to give myself some room. Let's consider a sequence of current loops. And so we'll draw 3 of them. And I'll draw them in the same orientation as before. So draw one here. We'll draw another one here and another one here. And there we go. All right. And so we'll have the current looping up in front of us. All right. So we'll call this 1, 2, and 3. And what we'll do is I'm going to find the net magnetic field at this point that sits in the plane of loop number 2. All right. So loop number 2, we'll start with number 2. By the right-hand rule, there's going to be some magnetic field that at that point is going off to the left. Okay, so this is our B2. Now, let's think of, say, this one. Well, it's making field lines that are going to be curling around like so. And so at this point, it has a magnetic field B3 that looks something like this, right? I can't draw it perfectly, but it's something like that. I've drawn B3 a little bit shorter than B2 because the source of the current is further away, and so we expect the magnetic field to be weaker. And then if I was to draw the field due to B1, loop 1, it's going to have something, well, let's see, something that's doing a little bit better than that, I think. So there's going to be some kind of field that's looping around like so. And so at this point, the B1 is something like this. And if you look at B1 and 3, they're components that are vertical, but opposite, and about the same size and magnitude. And so they end up canceling. Their horizontal components add up. And in fact, they add up to B2. And so what this seems to be indicating is that we're going to have a strong horizontal magnetic field inside the coils and with almost no vertical component. So inside the solenoid, the horizontal B field is strong, while the vertical component vanishes. All right. What I'd like to do is I'd like to try to see if we can consider a point that's outside of these loops. Whoops. Hey, why didn't you move? All right. So let's take a point that's over here. Well, what is the red one, the loop 2, going to do? The field is coming around and then it's looping back that way. So what we end up with is something like a B2 is something like this. If we were to pick the B3 contribution, what's it going to be doing? It's going to make a field that's kind of looping around something like this. And so B3, it's like so. Again, I tried to make B3 a little shorter than B2. Maybe I made it a bit too big there. There's B3. All right. And then what is B1 doing? It's making a magnetic field that's kind of along this direction. And so B1 is something like this. Well, in some ways, this is pretty similar. B3 and B1 have vertical components that cancel and horizontal components that add. It's just that their horizontal components add up to cancel with the B2. So outside the solenoid, B net is approximately 0. Now, of course, this is not rigorous. This is just kind of drawing by hand some of those fields. But if you were to do this very carefully for these current loops, you would find that this cancellation would in fact work out. So let's see then if we can go back to our solenoid problem. So now let's apply Ampere's law to the solenoid. Okay, so I'll draw my solenoid again. So we had our current coils coming up like so. Okay, and then it's coming down. So here's our current. Okay, so the first thing I would do is I would say, by the right-hand rule, if I curl my fingers in the direction of the current, my thumb points to the left. And so I'm going to expect the magnetic field to be, well, first of all, I expect it to be 0 out here. But inside, I'm going to expect my magnetic field to be off to the left. Okay, and so here's B. Okay, so what are we going to do? The first thing we're going to do for Ampere's law is we're going to select an Amperian loop or an integration path like we were talking about earlier. Right at the start of class, we calculated the circulation for the field around a long straight wire. And what we have to do is pick a path to integrate around. And so what do we want from our path? Our path should be parallel or perpendicular to B, if possible. What else should it include? I would like everywhere along my path where B is not 0 or not perpendicular, I want B to be constant. So B should be constant when our path is parallel to B. And well, in fact, that's probably good enough. So those are the two conditions that I want to satisfy. In a region of space where B is 0, I don't care. I could choose my path to have any shape I want. So what kind of path should I choose for this solenoid? Well, so my integration path, I'm going to do a line integral. So it has to be a loop. So it has to be just a 2-dimensional loop. I can't have like a 3D shape like a cylinder. Yeah, I could do that. So suppose I did that. Suppose I put a loop around here. How much current is going through that loop? None, actually. If I made it perfectly parallel to that plane, and if my loops were perfectly parallel, so that's not going to work. What about if I wanted my loop to have part of it be parallel to the magnetic field? Where should I draw that? Yeah, so I've got my magnetic field, I know has a horizontal component to the left. So my path is going to have part of it at least be parallel to that magnetic field. All right. Now I need to make it a closed path. So what I'm gonna do is when I come out of the solenoid, I'm gonna make these parts of the path be perpendicular to B. I'm gonna do that so that when I have to evaluate B dot dl in Ampere's law, I want that to be easy. Okay, so we'll follow this around to 2, and this will be, say, part 4 of my path. And now that I'm out here, does it matter how I go from 2 to 4? Why doesn't it matter? Yeah, B is equal to 0. So when I do the B dot dl, B is always 0. So this part could have whatever shape you want. Now, usually you won't see it drawn like that, but it doesn't really matter. Okay. All right. So I'm just trying to emphasize a point. Okay. So that's step 1 is we selected our path and we tried to satisfy some of these criteria. All right. 2 is let's find I enclosed, or how much current passes through our Amperian loop. Okay. Well, if I have current I in my coil, how much current goes through my blue loop? If you like, for exactly how I've drawn it. Yeah, that's right. So 3 of our coils go through the loop. So it's 3 times I. In general, if I had a really tightly wound coil, then I would have a whole bunch of those loops going through my blue path. And so I would in general have n loops of the solenoid coil pass through the loop. And so therefore, I enclosed is equal to n times I. All right. So step 3 is to evaluate this B dot dl. Now for us, our path has 4 different parts to it. And so I have to break this up into 4 parts. Now, you could maybe see already that a bunch of them are going to be 0. So here's part 2, here's part 3, and here's part 4. Okay. So in 3 minutes, we can finish this up. What's going to be the line integral for path 3? 0. Path 3 is going to be 0 because B equals 0 everywhere. Everywhere on 3. All right. What about 2 and 4? Why? Yeah, it's perpendicular for part of the path, and it's 0 for the remaining part. So 2 and 4 are partially inside the solenoid where B is not equal to 0. But in that case, the DLs are perpendicular to the magnetic field. So B dot DL is going to be 0. And then part of those paths are outside the solenoid where there is no magnetic field. So this is going to be 0. Sorry, not that one, not that one. This is going to be 0 because B is perpendicular to DL inside the solenoid. and B is equal to 0 outside the solenoid. Okay, and likewise, this is 0 for the same reasons as 2. All right. So what we have then is B dot dl is just going to reduce to this one path integral. And B and dl are parallel to one another for path 1. So this is B dl. This is, since B is parallel to dl for path 1. And this is going to be equal to B dl. Why is that? Well, if we look at this, path 1 was chosen to be parallel to the axis of the solenoid. So I never move to a different position in the solenoid. I'm always the same distance from the axis or the same distance from the wall, and there's nothing that changes along the length. And so there's no reason to think that B will change along path 1. Okay, so this is, since 1 is the same position inside the solenoid. And what I really mean by that is, say, the same distance from solenoid axis, if you like. Okay, well, let's do one other thing then. Let's go here and say that part number 1 of our loop has a length L. Okay, so if we do that, then we would say this is equal to BL. This is the length of path 1. And that has to be equal to mu naught I enclosed. Okay, so finally, what we have is from B dot dl is equal to mu naught I enclosed. This is Ampere's law. The integral gave us B times L. Then we have mu naught I enclosed, which is n times I. And if we divide by L, B is mu naught n over L times I. And usually this n over L is given as a number of terms per unit length, little n, which is the number of terms per unit length, or it's the turn density, so that B equals mu naught n times I. And so that's just the magnitude. The direction we've already drawn is to the left. One nice thing about this result is that I'll finish in just 30 seconds, is there's no like position coordinates. So if I picked my path to be, say, up here instead for path 1, nothing would have changed in the calculation. We would have got the same result. Or if I picked path 1 to go right through the center of the solenoid, nothing would have changed in the calculation. And so what this tells us is that inside the solenoid, the magnetic field is uniform, which is very convenient. So E inside the solenoid is uniform. And so if you think of a capacitor, think back to capacitors, these two charged plates that were held at a fixed distance away from each other, one's positive, one's negative. It created a uniform electric field between the plates, and E was equal to 0 outside. So the solenoid is the magnetic analog of that. The magnetic field is uniform inside the solenoid and zero outside. So we talked about problems involving firing electrons through a uniform magnetic field. Well, here's one way of making a uniform magnetic field. And in fact, you can make quite strong fields in this way because this turn density, you can make very large. You can get very fine wire, you wind your windings really close, and then you can do multiple layers. And so your density of turns could be almost arbitrarily large. And so you can get very large magnetic fields in this way. In fact, what they do in some situations, if you want massive magnetic fields, you make your windings out of superconducting wire, you cool it down in like liquid helium, and now I can put in extremely large currents and dissipate no power, and I could get like really large, like 10 and 20 Tesla kind of fields, which is very big. All right, cool. Thanks very much. We will see you on Wednesday. Hope you have a good afternoon.